Hello, students, and welcome back. We are ready to start our second semester of calculus, and as I have been telling you, the second semester is the reverse of the first semester. So we will be starting with the derivative and working our way backwards to find the original problem. And this process is known as anti-differentiation or indefinite integration. So we have a couple of forms that I want you to be aware of. This is what we've been using in the first semester. So dy dx equals a function. And what we're going to do is to split the dx away and bring it to a position beside the f of x. And when we write it that way, we are looking at differential form. So as I said before, the operation that you'll be performing is known as anti-differentiation or indefinite integration. So these would be a couple of new words for you. Indefinite integration. Later on, we will distinguish between indefinite and definite integration. So the new symbol that you will use is this symbol that kind of looks like NS, and it's called the integral sign. What you are integrating is known as the integrand. So all of this expression right here is known as the integrand. The dx is the variable of integration. So that's what you're integrating with respect to, and that will be the variable that will be in your final answer. And when you perform this integration, your answer will be the original function and a constant added on. So it'll be the original function and a constant. So maybe that will let you start to see why it's called indefinite, because you'll find out that when you perform integration, you end up with a family of answers that are all related by that original function, and they just slide up and down the y-axis. So these are your opening vocabulary words, and I thought it would just be easier to have those already written for you. So now I'm going to switch to a screen where I'll do some writing. And that'll be toward the bottom of your page. So I do want you to get the idea of this inverse operation. So the antiderivative of f prime of x, the antiderivative of the derivative, should give you the original function plus a constant. So just to do a quick illustration of this, without showing you any kind of formulas, let's just think about this first example, the antiderivative of 2x with respect to x, 2x dx. Well, so you have to think about what function would have a derivative of 2x. So what would give you f prime equaling 2x? And so if you think about it, the original function f of x could be, so think about what happens to the exponent. It moves in front, so we would need something to have an exponent of 2. 2x squared, or excuse me, x squared would have a derivative of 2x. But, and so I'm going to put x squared there. But it's also true that x squared plus 1 would have a derivative of 2x, or x squared minus 15 would have a derivative of 2x. And therefore, we will add an unknown constant to create that family of graphs that has a derivative of 2x. So to drive home the fact that this is an inverse operation, it should be true that if you do the derivative of the integral, you end up with what we started with originally. So what we were originally doing the integration of, or in other words, in this problem, 2x. So let's look at that. The derivative of the antiderivative. So that would be the derivative of the integral of 2x dx. And so that would be the derivative with respect to x of what we found out was our answer. So we found out that this answer was x squared plus c, and the derivative of x squared plus c is 2x, which is what we originally started with. So it is an inverse relationship. The derivative undoes the integral undoes the derivative. So this is the introduction to what we're going to be doing. In this second semester, we're going to do things a little bit backwards from how we did in the first semester. I'm going to go ahead and give you the shortcut rules, and then later on we will see the foundation that this was built upon. So you'll need to switch to your paper that has the differentiation and integration rules. And I'll be bringing that up on the screen for us. And the integration rules, if we were doing this live in class, I would have you fill out all of the derivatives and then see how the integration rule is related to that. So I'll just talk about it in this way. The derivative of a constant is 0. So the antiderivative of 0 with respect to x is c. The derivative of a constant times x is just the coefficient k. And so the antiderivative of just a number, a non-zero number, is going to be kx plus c. Then you have a couple of rules, 3 and 4, that are similar for derivatives and integrals, in that you may pull out the constant and then do the derivative. You may also, in Rule 3, pull out the constant and then do the integration. In Rule 4, you'll see that differentiation is distributive, and so is integration. It is distributive for you to integrate the f of x and then the g of x. So number 5 on the differentiation side is your power rule. And so we have a power rule for integration as well. Okay, so this is your power rule for derivatives, and this is your power rule for integration. And so the rule is that you will raise the x to the n plus 1 power. So whatever the exponent is, you're going to add 1. And then you'll divide that entire expression by that new power, n plus 1. And then, of course, add a constant. You do have to have the warning that n cannot equal -1, because that would create 0 in the denominator. And then your remaining rules are related to the derivatives. So hopefully you can get those derivatives back in your memory, because I think you'll need those in order to be able to come up with the integrals. So I'm going to clear the ink and scroll up just a bit so that you can see all of the trig ones. So the derivative of sine is cosine. The antiderivative of cosine is sine of x. The derivative of cosine is negative sine. The antiderivative of sine is negative cosine of x. I'll give you a hint like I gave in the first semester, but it is a tad bit different. Any answer that begins with co will be negative. So the antiderivative of sine of x is negative cosine of x plus c. The antiderivative of cosecant squared of x is negative cotangent of x plus c. Antiderivative of cosecant of x, cotangent of x, is negative cosecant of x plus c. So hopefully as you are looking, you can see the relationship between the derivatives and the antiderivatives. And I'd say that the most important thing that you have to realize is with integration, just as with any inverse operation, your rules are more strict. So the form that the integrand is written in has to be an exact match for the formula. So in other words, you don't see an integral for the secant of x because we don't have one. We do have one for secant squared of x dx. So the integrand has to be rewritten in a form that fits the rules. I think that's going to be the most challenging part of our lessons, is getting them rewritten so that they fit the rules. So some guidelines. Of course, you want to rewrite using negative and fraction exponents. You want to separate out fractions, multiply out products. So in other words, there is no product rule. You need to divide out your quotients. There is no quotient rule. You need single terms, and then you're going to need to use the power rule. So you've got to get number 5 where you know what to do, because that will be the rule that you'll follow. So I want you to keep this paper in a place where you can readily refer to it. It's got your rules that you'll use for the rest of this semester. So now we'll go back to the notes page, to the back side, and we're going to work our way through the different examples. Now, I've got it set up so that, well, hang on, I'm going to make it just a little bit bigger. There. You can see that we need to often rewrite, then integrate, and then simplify. So I tried to set things up so that you could see that. So for problem number 1, the rewrite, when you're rewriting it, include the integral sign. You have x times the square root of x. So that would be 1 over, and then we could add those exponents up. So this is a 1 and a 1/2. That would be 3/2. And then we would need to get that out of the denominator. So one more rewrite, your final rewrite would be x to the negative 3/2 dx. I am very picky about you writing the dx. It tells you what variable you are integrating with respect to. So even though you may see it as inconsequential, later on, it's going to have a purpose. So get in the habit of writing that dx at the end of your integration sign. So now that you have the rewrite completed, we'll do the power rule. So the power rule says that your answer, and if you want to write it as f of x equals, you can. I don't usually make a distinction between using a capital F and a lowercase f, so lowercase is fine. You'll have x, and the power rule says that you're going to add 1 to the exponent, and then you'll divide that entire expression by that value. So -3/2 plus 1. And then now that you're writing the function, it will be plus c. So no longer the dx, but rather the constant. And then finally, you're going to simplify that expression. So we're going to write our final answers without negative exponents. So f of x would equal x to the -1/2, and then the denominator would be -1/2 plus c. I would also like for you to not have complex fractions. So I don't want to leave the -1/2 in the denominator. If you're dividing by -1/2, that is the same as multiplying by its reciprocal. So that would be -2x to the -1/2 plus c. And then to get the negative exponent taken care of, you could either put it in a square root, which is how I'm going to do it. And since it's a negative exponent, the square root will be in the denominator. So -2 over the square root of x plus c. And that would be the original problem. Now, one nice thing is now that you know both integration and differentiation, you should be able to find a line like this line right here and just quickly check your answer. So if you did the derivative of the line with the red arrow, you would take -1/2 times -2, and that would be 1x, and then you'd subtract 1 from the exponent, and that would be -3/2. So if you are just going to, if you check your work, and you don't have to, but it's not a bad habit, f prime would be 1x to the -3/2, and your plus c, that derivative is just 0. And so is that what we had for the original problem? And yes, it is. So there's a good way to check your answer. All right, let's move on to our second one. So on the second problem, now we have a quotient. There is no quotient rule. So you will need to rewrite this as separated terms. Since you have a monomial denominator, we can separate this out by integrating x squared over x to the 4th plus, and then 2x over x to the 4th minus 3 over x to the 4th. And remember that you're integrating with respect to x. Then we could simplify using negative exponents. So this would be x to the -2 plus 2x to the -3 power minus 3x to the -4 power dx. It's a good idea while you're learning to maybe label what you're doing so that you don't mistake having done that line and thinking that you've done the integration. So now the integration, we're going to use the power rule. So f of x would equal x to the negative 2 plus 1 over negative 2 plus 1 plus 2 times x to the negative 3 plus 1 all over negative 3 plus 1, and then minus 3x to the negative 4 plus 1 all over negative 4 plus 1. And then remember to put a plus c. That's often something that takes some getting used to. So now we will simplify. Your denominator is negative 2 plus 1. That would be negative 1. So something divided by negative 1 is just going to be negative 1x. And then we'll have our exponent to the negative 1 power. Here you have 2 in your second term, 2 divided by negative 2. That will be negative 1x to the negative 2 power. And then in the last term, you have negative 3 divided by negative 3. That's going to be plus 1x to the negative 3 power plus c. And then if we write it without negative exponents, and again, this is f of x. So f of x will equal negative 1 over x minus 1 over x to the second plus 1 over x to the third plus c. And it may be the case that later on we have to get common denominators, but for this lesson, we will leave our answer in that separated form. So those are your first two, and are two good examples of the rewriting that needs to happen to do your integration. So I'm going to clear the screen and we'll scroll up and do the last two. So on the last two, I didn't put your steps, but the steps are always there. However, on problem number 3, this is one that can be confusing. So think about what it's asking. You're asking what has a derivative of 14. And so it would have to be something times a variable. Now, this is one of your rules. So this is where the dt is important because your variable is a t. So it will be f of t equals, and then 14t plus c. So no simplifying needed, but you can think, if we do the derivative of 14t, we get 14. And finally, if you have a trig function mixed in with something that is not a trig function, you might think about rewriting using the distributive idea. So we could integrate theta to the second d theta plus, and then integrate secant squared of theta d theta. So since we're integrating with respect to theta, we'll use our power rule in this first one. So that would be theta to the 2 plus 1 power over 2 plus 1 plus, and then our derivative, and this could be f of theta. And you don't always have to put that. I don't always have it, but it is a good little habit. And then for the secant squared of theta, the antiderivative of secant squared, so you have to think, what has a derivative of secant squared? Well, that would be tangent of theta. and then plus your constant. So just simplifying, f of theta would equal theta to the third over 3 plus the tangent of theta plus c. And there you have your examples. I hope that you get along well with this first assignment, and be sure to seek help, especially early on, so that we get off on the right foot.